Okay, so now I'm going to assume that you're comfortable with the idea of a conjugate analysis, conjugate Bayesian analysis for, let's say, the binomial mixture proportion using a beta prior. And we're going to move on to the idea of empirical Bayes and shrinkage. And we're basically going to give you an overview of that based on the blog post that's available here. I think this is a very nice intuitive introduction to empirical Bayes based on some baseball data. So I'm going to click on that. Okay, so this is by David Robinson, and here's the idea: is Dave considers some data on baseball players. So the basic way that people measure how good a baseball player is in terms of their batting performance, at least, is what proportion of the times that they are at bat. So at bat is where they go up to face the pitcher. They stand there with their bat. They're at bat, and they can either get a hit or they can miss. Actually, they get several attempts, but if they miss 3 times, they're out and they get no hit. If they hit it one of the 3 before missing 3 times, they get what's called a hit. And so their batting percentage is just the proportion of times that they're at bat that they get a hit. Okay, so that's called the batting percentage. Okay, so if I go up to face a pitcher 10 times, and 3 of those times I get a hit, and 7 of those times I do not get a hit, I would have a batting average across those 10 attempts of 0.3. Okay. So these batting averages are used as a way of kind of ranking baseball players. So what Dave looks at here is a data set where he starts by doing some basic things like filtering out the pitchers and averaging over years here. And he starts by looking at, well, which batters had the best batting averages. Okay. So that's just I guess that's just the top of the data set. Here are the ones with the highest batting average when he goes and looks at them. And so H here is the number of hits, and AB here is the number of at-bats. So their batting average is H, the number of hits, divided by the number of at-bats. So the problem that he runs into when he does this is that the individuals with the highest batting average, these individuals all had a batting average of 1, actually, which is excellent. It means they hit at every at-bat. If you look at that, you can see they only had a very, very small number of at-bats. So really, these are not actually the best batters. These are the batters that had very, very small number of at-bats and just happened to get a hit. Whereas these guys, this is the other end, looking at the ones that have the worst batting average, they're also the ones that had very, very few at-bats that happened to have no hits. So just to provide a bit of context, firstly, professional baseball players, they wouldn't be in the league if they actually had a batting average of 0. And no one actually has a batting average of 1. Even the best baseball players over a season or 2 have batting averages. 0.3 is a very good batting average. So 1 is a ridiculously high batting average. And what you can see here is that the idea here is that the maximum likelihood of this individual's, one way of thinking about it is that the maximum likelihood estimate of Jeff Bannister's batting average, which is 1, is not actually a very plausible estimate of their batting average. Imagine, for example, to make it concrete, that you were being asked to predict what Jeff Bannister's average would be over next season based on data in, say, a current season where he'd only batted once, well, essentially the fact that he batted only once says that you don't have much information about what his batting average is. Okay. So, and in particular, given that we know that most professional baseball players don't have, I've told you that most baseball players don't have a batting average above 0.3, you would be crazy to guess that he would have a batting average of 1 next season. Okay, so you can maybe start to see the idea that, or the hint here, that we might want to be doing a Bayesian analysis here, where we combine some kind of prior notion that, you know, 1 is an implausible batting average with these data here, which you might think about modeling as a binomial, as binomial data. So we'll get back to that idea later, but just keep that in your head. Okay, so the basic idea though here is that the maximum likelihood estimate, which for these individuals is 1, it's at bats divided by H, and for these individuals is 0. In both cases, those maximum likelihood estimates are not really very plausible estimates for the batting proportion of those individuals, say, for a future season. Okay, so that average is a really crummy estimate, is what the blog post says. Okay, so here you go. This is a distribution of the empirical batting averages across all the across lots of players. Anyway, not quite all of them. He's filtered out here players who have very few at bats. So if you see here, he's filtered out the individuals who have fewer than 500 at bats total. These data he's looking at are averaged over lots of seasons, or summed over lots of seasons. So many of the individuals, he has lots of individuals who have hundreds or thousands of at bats. And you can see what I said before is true, that 0.3 is a pretty good batting average, right? Of the individuals that had more than 500 at bats, relatively few get a batting average of more than 0.3, and the average is somewhere around 0.7 here. So here's the idea. Essentially, this distribution here gives us a prior on what we think the batting average of a, let's say, an individual whose data we haven't seen yet. If we had to guess what their batting average would be, an individual from the same league, let's say, as the individuals that we've taken here, we might use this as a prior distribution for what we might expect their batting average to be. And if we had to guess what their batting average was, a point estimate might be around 0.27 before having observed any data. So the intuition is that, you know, for these individuals where actually we have relatively few at bats, we have very little data, we would actually be better off just using that prior, this prior maybe, as an estimate of their batting average than using the maximum likelihood estimate based on very little data. So that's where we're going here. Okay, so notice that we're kind of estimating the prior from the data. So that's why this approach, or the approach we're going to look at, is called empirical Bayes, because we're using the data to estimate a quote's prior, right? So that's, keep that in mind as well. Okay. So given these are binomial data, a natural choice of prior, as you should recall, is a beta distribution that just happens to make the computations nice and easy. So if we, here he's used X not as data, I guess, but as the batting average. So he's using a beta prior with some alpha 0 and alpha and beta 0 for his two parameters. And so what he's done here is he's come up with a way of estimating alpha 0 and beta 0 from the data. And he's done it, he's basically just fit it to these data And we're going to come up with a slightly better way of doing that in the, down the line. What he's done is good enough for now and gives you the intuition, but we'll talk about why it's not quite right, I guess, later. But for now, he's basically fit this red line to this histogram of individuals who have lots of data and come up with a prior that's roughly beta 78 and 224, or 79 and 225. And then the idea is that you, having done that, you can use that to combine that with your data on each individual to do their, to estimate their batting average. So notice here, this, I guess this is a hypothetical batter that went up 1,000 times. That's 1,000 at bats, and they got 300 hits. So their batting average, their MLE is 0.3, and they went up a lot of times. So when you do the Bayesian analysis, what you find is that the posterior mean, that's what he's computing here. So this is the posterior mean of his batting average is actually pretty close to the MLE. And that's the reason for that, is that he went up a lot of times, 1,000 times. So the data outwhelmed the prior and, or overwhelm the prior and dominate this posterior mean. Whereas this is an individual who only went up 10 times and got 4 hits. And even though so their batting average, their MLE is 40%, in this case, because he only went up 10 times, the prior is quite a bit more informative than the data. And so the estimate you get for this player is much closer to the prior mean than it is to the individual's MLE, which would have been 40%. So in other words, we estimate that this guy is a better batter than this one, essentially because 30. If you recall, he got 30% from 1,000 hits, and you can see that's pretty high. So that the individual compared with what a typical batter would get. So just because this individual happened to get 4 hits from 10 at bats, that's not enough to convince us that in the long run that batter would lie, in this tail here. So that's a basic idea. That the key idea we're going to try and get across here is that you can estimate a prior from the data. That's where we're going here. So that Dave, in his blog post here, did it in a particular way. We're going to make that more formal in a minute. But for now, that's the key idea, is to estimate the prior distribution from data on a large number of individuals. And then for any given individual, we can compute their posterior distribution using that prior. So what this graph here shows, this graph's kind of important to understand, is essentially this is the MLE on the x-axis, this labeled batting average. This is the MLE, which is the number of hits divided by the number of at-bats. And it's colored according to how many at-bats. So these dark colors here are ones that didn't have that many at-bats. And these lighter colors up here are ones that had a lot of at-bats. Okay. And then this is the empirical Bayes posterior mean estimate of each individual's batting average. So what you can see here is the ones that are the darker points, which are the ones with the fewer at-bats, actually end up changing quite a lot from the MLE. They're far from this y equals x line, whereas the ones with the most at-bats actually lie pretty close to the line. So that's kind of a first thing to see, that this is kind of consistent with this kind of analysis, where the individual with a large number of at-bats, their estimate is pretty close to the MLE, whereas the individual who had a small number of at-bats, their estimate is pretty close to the prior mean. And this comes back to the idea in Bayesian analysis that if the data are very informative, then the prior doesn't matter too much. But if the data are not very informative, that's the second case, then the estimates are kind of driven by the prior. So that's what's going on in this thing, in this picture. The other thing to note is that essentially all the estimates that's on the y-axis, all the empirical Bayes estimates are closer to this red dotted line than the MLEs are. So basically, if the MLE lies above the red dotted line, then the empirical Bayes method moves down towards the red dotted line. Whereas if the estimate is below the red dotted line, then the estimate moves up towards the red dotted line. So this, you can think of this as it's kind of shrinking all the estimates towards the red dotted line. So if you're, and the red dotted line is essentially the prior mean. Right? That is what we would guess someone's batting average was if we had no evidence at all, if we had no data and we only used our prior. So the intuition here, is that if their estimate is out here somewhere, then our prior pulls us towards the average, which is over here. Whereas if the estimate is down here below the average, then the prior pulls it up. And this idea that the estimates all get pulled towards a common value is sometimes called shrinkage. So often we shrink estimates towards 0, actually, but in this case we're shrinking them towards a common mean. In this case, around 0.26 or 0.27. So that's an important concept as well. Shrinkage. The idea is that you take estimates and you move it towards some kind of central value, which in this case is the prior mean. Okay, so as Robinson points out, this is super easy, actually. It almost feels like cheating, but I think it gets at the essence of the several key ideas. One key idea is we're going to estimate our prior from the data. We're going to use data on lots of baseball players, basically, to estimate what our prior should be on a baseball player's batting average. That's idea number one. And idea number two is the idea that Bayesian analysis often ends up kind of moderating the data with the prior, and as a result, you get what this kind of idea called shrinkage, where you move the data, the MLE, towards the prior mean. Okay, so those are the key ideas, and we've kind of waved our hands around the statistical details, and we're going to talk, actually he talks about how we could make it more complicated here. We're going to talk about how we can make these ideas a bit more rigorous in the next video.